because the other modes have a different GOI phase and they therefore resonate at a different frequency than the TEM00 mode which we want, not only does this mode cleaning cavity pick out and transmit only the light that has frequency that is within this narrow resonance. So it cleans the light in terms of its frequency. It also then cleans the light in terms of its transverse mode structure, because the only stuff that will go through is stuff that has the right GOI phase to resonate with the given chosen separation between the mirrors. And that will be only the desired TEM00 mode, plus some high order modes, rather high order modes that happen to be just close in GOI phase to this one. But generally your incoming light won't have hardly any of that very high order stuff. It has mostly the desired stuff and low order stuff that gets filtered out. Okay, any questions? Okay, then there's one more set of ideas that we're going to need in the coming weeks that I want to introduce. And these are ideas relative to the theory of random processes. It's the concept of spectral density, which I have talked about a little bit first term, but never really introduced in a quantitative sort of a way. Manipulation of spectral density by filtering and discussion of gravitational wave noise in terms of spectral densities. And so suppose that I have a function of time that may contain some signal in it, but it also contains some noise. And by containing some noise, what I mean actually is that it may wander in some manner that is unpredictable and random due to whatever the physical process that generated this signal being imperfect. We really haven't made it behave precisely the way you would have liked it to behave. So examples of what this quantity might be is it might just be the X component of the electric field that is coming out of the laser. So the laser light coming out of here is not really clean. You would like it to be sinusoidal at frequency omega e, but it wanders some. The frequency wanders some, the amplitude wanders some. And so this contains, in addition to what you want, it also contains some wandering stuff. It might be the intensity of the light coming out of the laser, or the application that we will want is the intensity of the light coming into the photodetector down here in the interferometer. If it's the intensity of the light coming into the photodetector, we know that that intensity, its variations, can be interpreted as caused by variations in the phase difference between the light that is coming back in those two beams to the beam splitter, as I discussed yesterday, which in turn can be interpreted as due to changes in the arm lengths of the cavities, which have induced these changes in phase. But the changes in the arm lengths of the cavities can be produced by a gravitational wave. And so when we see some oscillations in the intensity going into the photodiode, from those, knowing, having analyzed the interferometer, we can infer a gravitational wave field, H of t, or the plus polarization, H plus of t, if the waves are coming down perpendicular to here, or some particular mixture of H plus and H cross if the waves are coming in from some other direction. But we can infer some H of t for a gravitational wave field that's exciting the cavity. And so this I of t fed into some formulas that we will derive gives us some H of t, an inferred gravitational wave. But this, because I of t has noise in it, H of t will have noise in it. And so it has this wandering random noise, which is coming from all kinds of things that influence the interferometer in ways we don't want them to. And so when I think of this y of t, which is my random process, plus some signal, we hope some signal, it then can be thought of as examples, the inferred gravitational wave signal coming out of the interferometer, the intensity of the light going into the photodiode, to which this quantity is proportional, the electric field coming out of the laser, as then specific examples. And we want to develop mathematical tools for discussing the noise that is contained in these random processes. Now, for that purpose, I'm going to always, when I deal with a random process, I'm going to remove the mean. Just the mean, the time average, is a little, obviously doesn't contain noise. If it's there because you wanted it to be there, or it's there because you didn't want it to be there, you didn't quite get rid of it, but it's not going to influence the time varying part of the field. It's the time varying part of the field that's going to contain your signal. And so it's mathematically convenient just to get rid of the mean. And so I'm going to always get rid of the mean. And so this guy has vanishing mean. That just enables me to avoid some complications in various formulas. Now, one thing that we can do with a random process is we can Fourier analyze it. And so we can compute a corresponding y tilde of f. My conventions for Fourier analysis will be those that are used by the signal processing community, except that I use the sign for the exponentials of the physics community. So let me, and I think this is fairly standard by people in gravitational wave research, that they use this set of signs, so I'm not sure. Physicist signs and signal processing community's choice of factors of 2 pi. So a physicist normally would write this at 2 pi f as omega, gravity wave frequency, or, well, frequency omega. And instead of this df, they would have d omega over 2 pi. So in any physics text, you always have a factor of 2 pi floating around in here somewhere. The signal processing community has chosen to do things in terms of the frequency, not the angular frequency. That way they've got a df here instead of a d omega over 2 pi, and you don't have to worry about the factors of 2 pi. The signal processing community also, following engineers' practices, has these signs flipped on the exponentials, if you go read signal processing books. But this is what I will use. Now, also of use when we talk about random processes is Parseval's theorem, which tells us that the integral from minus infinity to plus infinity of y of t squared dt, y is, for me, y is always going to be real. All my y's are real: gravity wave signal, light intensity, the electric field. And so y of t squared, I don't have to put an absolute value sign on there, is the integral from minus infinity to infinity of y tilde of f absolute value squared df, because y tilde is in general going to be complex. The fact that y is real means that y tilde of f is equal to minus y tilde star of minus f. That is, when you just go from f to minus f, you just change the sign of the Fourier transform on f. That's the statement that guarantees that y is real. And that means that since only the modulus of y appears in Parseval's theorem, and in fact all we're ever going to be concerned about as we talk about noise is the moduli of these Fourier transforms. That means that we are free, if we wish, to take the frequency to always be positive. Fold negative frequencies into positive frequencies. That is, the contribution from minus f is the same as from f. And so I can write this as twice the integral from 0 to infinity of y tilde of f squared df. And so that's Parseval's theorem. And these factors of 2 will start floating around because following a convention that seems to be fairly universal in the gravity wave community, we will take F to be only positive. People in other communities, such as the quantum theory of measurement community, usually take F to run from minus infinity to plus infinity. Okay. Now, these are just standard formulas, and they are formulas that are not actually very useful for a random process, because of the fact that the random processes that we are considering, well, you have a choice. They may go on and on forever, and if they go on and on forever, then this integral is going to diverge. In practice, they don't go on and on forever. In practice, what we're dealing with is, say, the noise out of the laser. You turn the laser on, and it sort of settles down into some operating state, and then it has some sort of noise associated with it. But a few hours later, it may change temperature or something, and may change slightly its noise characteristics. And so we're really interested in being able to discuss the changes over time of the noise characteristics, changes on times that are very long compared to the frequencies that are present in this random process. Changes generally on times of minutes or hours or days. And so what we really want to do is do Fourier transforms, not of the full random process that lasts forever, but of something where we truncate it. We just consider this random process, the output of the laser, for say an hour. And we take a Fourier transform of it for an hour, or for a few hours, or for a day. And then we do the same thing the next day, and we compare the results. That means there's some arbitrariness in here in how long we take to do the random process, and the overall amplitude of this is going to depend on that. And so I want to get rid of that dependence. And so what I want to do is the following. I want to consider the random process and truncate it so that I define a y subscript capital T of time, which is 0 for times less than capital T over 2. I'm sorry, modulus of the time is less than capital T over 2. It's equal to y of t for, I'm sorry, bigger than, for times whose modulus is less than capital T over 2. That is, the random process is something as a function of time. I'm plotting y up. It wanders around. I pick some central time, I call it t equals 0, about which I want to study the noise in here. I go back a distance, or time, capital T over 2, where capital T might be an hour, and I just cut this off and set it to 0 before that. I go forward an hour, and I cut this off and set it to 0 after that. So I just truncated the random process so its duration is some arbitrarily chosen time that is a time scale on which I want to do averaging in order to discuss the noise in this random process. I can then go in and look at the modulus of the Fourier transform of this quantity. Let me just put subscript capital T's on Parseval's theorem here. I still do these integrals from minus infinity to plus infinity. But in this integral, I only get contributions from the time interval from minus t over 2 to plus t over 2. Now we know in this integral, if the noise is more or less stationary, the value that I will get for this integral in Parseval's theorem is going to be proportional to t. If I double t, I'll get twice as big a value of this integral. And so what I want to do is renormalize my quantity that I'm going to use to study the noise by dividing through by this capital T. So let me take 1 over t times this. This is still just Parseval's theorem. 1 over t here. I have a 2 over t there. And I now have, in Parseval's theorem, something that on the left-hand side, I have a quantity which in fact is the mean square value of y. That is, I square y and I average it over time, over the time from minus t over 2 to plus t over 2. And so that's y squared mean. It's averaged over this time duration, capital T, which would say 2 hours. But the mean of y itself vanishes. I chose it that way. And so this quantity, in fact, is just equal to delta y squared. It's the variance of y. Or it's the square of the RMS value of y as it oscillates. It's the mean square value of y's oscillations. So that's really nice. That's what I have on the left-hand side. The thing over here on the right-hand side tells me how these oscillations in this random process contribute to the mean square variations. It tells me how much contribution I get from various frequencies. So that's an interesting thing to know. How much contribution do I get from various frequencies to the mean square variations of this quantity y? And so that motivates me to define the quantity that I'm integrating over here. This 2 over t times that Fourier transform. I'm going to define that as my measure of the noise power. That's going to be S sub y of f. And so let me write it explicitly. That's 2 over capital T, the integral from minus t over 2 to plus t over 2. I'm just writing down the formula for the Fourier transform, and I only integrate from minus t over 2 to plus t over 2 because this is y truncated to that particular time interval. Y of t e to the I 2 pi ft dt, and then I want this quantity absolute value squared. And so this is called the spectral density of y. And by virtue of Parseval's theorem, we see that if we take the integral of the spectral density of y over all frequencies from 0 to infinity, we find out the mean square variations of y actually during this time interval, capital T, that I've used in order to characterize the noise. And as I said before, if you're interested in in how much power there is, and by how much power I mean how much contribution there is to these mean square variations in some specific frequency band, then I just integrate over that small frequency band. And in particular, if I have some small frequency band delta f, over which the spectral density is nearly constant, and if I were to take my random process and filter it in order to get rid of all components, so all oscillations that are in y that are outside that small frequency band, I would then have RMS variations that would just be this integral over that small frequency band itself. And I would have then the delta y, the RMS squared, or the mean square variations, over after I have filtered it so that I have kept only the noise and signal in this small frequency band, is just going to be equal to S sub y evaluated at the central frequency of that small frequency band times delta f. Or if I want the RMS fluctuations after I have filtered out all oscillations outside that frequency band, I just take a square root. And I think I've written down a formula like that, and we used it a little bit when we talked about gravity wave noise and signals, first term. Okay. Let me talk, I've talked in words here about filtering. Let me talk mathematically about filtering. An example of a filtering of a random process is to send in light into this mode cleaning cavity. It has an electric field that is oscillating, and it's a little noisy, so it's oscillating with some oscillations noise oscillations that are outside the resonant frequency band of this cavity, as well as some excitations that are inside that resonant frequency band. And what this cavity does is it does a filtering in the following mathematical sense, that the y that comes out is equal to the y that goes in, or it's equal to an integral of some filter kernel k of t minus t prime times the y that goes in dt prime. This is just a statement from minus infinity to plus infinity. This is just a statement that the output is linear in the input. And this is the most general form, the most general mathematical form of a transfer from some input to some output where the output is linear in the input. And there is no absolute time introduced anywhere. This depends only on difference between the time at which you evaluate the output and when you evaluate the input. So this is a filter that is stationary in the sense that the filter itself does not pick out any preferred absolute time. So there will be some k of t minus t prime that actually characterizes the this cavity as a filter that tells you the electric field coming out in terms of the electric field going in, and you could work that out if you wished. But it's really nice that what is going on here mathematically is a convolution. And in Fourier transform theory, we know that the Fourier transform of a convolution is just the product of the Fourier transform of the two functions that appear in the convolution. So this k tilde of f, you compute the Fourier transform by taking the Fourier transform regarding that as some time tau, and you use the usual formula for a Fourier transform on tau. So that's a theorem from Fourier transforms. But since the spectral density is just built out of a Fourier transform, where you've actually done some truncation at time over this time capital T, but this time capital T is assumed to be very long compared to the time intervals over which this kernel is acting. So that basically means that then that y capital T out will be the same as y capital T in, aside from the filter function. That this formula will still be true when you've done the truncation in time of these of the input and output. Or correspondingly, if I take the absolute value squared of this, the absolute value squared of that, absolute value squared of this, that's still true. Or that means that spectral density of y out, frequency f, is just the modulus of the Fourier transform of the filter function times the spectral density of the y in, frequency f. So that's a very nice relation that enables you, once you have understood any kind of filtering, and remember filtering is just the most general linear process can be written as a filter. If y is the time derivative of y out is the time derivative of y in, you can figure out what this k is and so forth. So this enables you to fairly easily talk about how the spectral densities of noise change when you do a filtering. Now, an example of a random process that's going to be important for us is photon shock noise. So if I have my gravitational wave detector, light coming in through a light power recycling cavity, and then goes into these arms, and comes back out, and goes down to the photodiode. There will be a gravity wave signal coming into the photodiode, and along with this gravity wave signal, there will be noise, and they are both carried by a light intensity, which is measured by the photodiode. And I'm going to give you an exercise that builds on all the tools that I've given you in the lecture on Monday and today, an exercise to compute what the gravity wave signal is if some h of t gravity wave with plus polarization acts, shortening this arm, lengthening that, so shortening and lengthening. It acts as an h of t. You get an output signal then in I that's proportional to h of t, or that at least that is a linear functional of h of t, speaking more precisely. So there is some filter function that is described by the whole gravity wave detector that goes from h of t to something linear in it, which is the I of t. But this I of t also contains noise, and among the kinds of noise it contains is the photon shot noise. And so knowing how h is contained in here, if we can figure out what the photon shot noise is in this light intensity, we can then figure out the corresponding spectral density of h. When we do the data analysis to go from I of t to a measured h of t, we can see what that spectral density of h is. So what we need to understand is the shot noise in a light beam that is coming into the photodiode. Now this light beam consists of individual photons. Each photon comes into the photodiode, and if the photodiode has perfect efficiency, another little issue that a theorist always assumes perfect efficiency, and the experimenters worry about the efficiency, then each photon comes in and it generates some electrons that flow through and get measured by a circuit. And so I of t consists of pulses of incoming light intensity, one pulse associated with each photon. So we don't know precisely what the pulses are. These photons are really quantum mechanical animals anyway, and the pulses are going to depend on the actual quantum state of the light. But the pulses will have some duration, tau pulse. Each pulse will have, pulse I will have, or pulse j will have an arrival time t sub j, at which it begins to arrive at the photodiode. And then it'll last for some time, tau pulse. And the duration, tau pulse, of each pulse is going to always be small compared to 1 over the gravity wave frequencies that were of concern to us. That is small compared to, say, 1 millisecond. After all, the frequency of the light is about 10 to the 15 hertz. Well, 3 times 10 to the 14 hertz. So something that would last a millisecond would be lasting for something like 10 to the 12 light periods. And you just don't get light that has pulses where the individual photons last that long. So the pulse time is small compared to this, and so that means correspondingly that if I Fourier transform, so this is the light from a given pulse, ij of t. If I look at ij Fourier transform at frequency f, that's going to have some form that will die out as a function of frequency at a frequency 1 over tau pulse. And this is going to be huge compared to 1,000 hertz. The Fourier transform is something that has that shape, lasts for a time 1 over the duration of the pulse. I'm appealing to something you should know about Fourier transforms. And so the gravity wave frequency is of interest to us are sitting way down here, close to 0 frequency compared to the Fourier transform of the pulse. Now let's ask, what is the spectral density of the full light intensity coming into the photodiode? So that full light intensity is a sum over all the pulses of ij of t minus tj. Let me write it that way. Tj is the arrival time of the pulse. Okay. And the pulses may have different shapes. They may have the same shape, may have different shapes. That's why I put a subscript j on here to allow for different shapes. If I compute the Fourier transform of this, well, first I want to truncate it to my time interval that I need in order to discuss a spectral density. So I truncate it to a time interval of of about an hour around some central time. That means that I include only those pulses that arrive during that hour, and we don't include any others. Okay. If I then take a Fourier transform of this and an absolute value squared, I'm going to get the sum over j and k of ij tilde of f. There's going to be an e to the I 2 pi ftj as well in here. That's just a phase factor. Times an I tilde k of f star e to the minus I 2 pi ftk. These phase factors are just coming from my offset of the time of arrival. It's not terribly important. But when I take the absolute value squared, I basically have a sum then over a product of these guys with each other. But the key point is that the different pulses are not correlated with each other. And so pulse number 1 and pulse number 3, in their product, they will give some number, but that will be canceled on average by pulse number 5 beating against pulse number 7. That is, all of these product terms are going to basically wipe each other out because the pulses are uncorrelated. I'm assuming uncorrelated light in these pulses. And so all that I get is the sum over j. I only get those terms where j is equal to k, and I wind up with I tilde t at frequency f squared is just the sum over all the pulses of I j tilde of f absolute value squared. But I'm interested only in frequencies that are down very near zero frequency, and so I today as well just evaluate this at zero frequency because this Fourier transform lasts for so long. But ij tilde at zero frequency is just the integral of ij e to the I 2 pi ft, where f is 0, times dt. So it's just the integral of the light intensity associated with pulse j over time. That's just the energy in the pulse, and it's the energy of one photon, so it's h bar omega e. And so this Fourier transform, absolute value squared, is just equal to the sum over h bar omega e, sum of h bar omega e over all of the pulses. So it's just the total number of pulses, or the number of photons that arrive during time t, multiplied by h bar omega e. That's what this is. And to get our spectral density, we want to take 2 over that time times this quantity I just computed. And so the spectral density of I, or S sub I of f, is just equal to 2 over time, the number of photons that I get in time t, times h bar, times the energy of each photon. Very simple. But 2 times the number of photons divided by the duration during which I collect them is just twice the rate of incoming photons. So we have the simple formula that for any light beam, assuming these photons are uncorrelated, as I did, the spectral density of the light intensity in the beam is twice the rate of photon arrival times h bar omega e, or I can write it as twice the intensity of the beam, that's the rate of energy that comes in, divided by the energy of each photon, times, have I done something? This is such a simple calculation. That's right. twice the intensity of the light divided by h bar omega e times the energy h bar omega e. So it's just equal to twice the intensity of the light. And is that right? Suddenly I don't feel right about it, but it's all trivial. I think it must be. Let's just look at dimensions. No, I fouled up. So this is the square. This is the square of the Fourier transform. When I compute that, I get an h bar omega e, and so I have an h bar omega e squared. Okay. So that's, my notes are wrong. So this is the square of that Fourier transform. The Fourier transform itself was h bar omega e. So now I'm getting the right answer. So this is squared. Okay. So spectral density of the intensity fluctuations is twice the intensity, or the light power, times the energy of each quantum. And it's a standard result for any shot noise, where the individual shots are, have quantized energy, so they all have the same amount of energy, and the shots come in on time scales very short compared to 1 over the frequencies that we're interested in. Okay. So that then becomes a key input for being able to compute the gravity wave noise associated with an interferometer. And I will give you then, on a problem set that will appear on the web hopefully by tomorrow night, and if not by Friday night, I will give you the actual formula for the noise in the idealized interferometer that I started out talking about on Wednesday. And I will lead you then through a not terribly complicated calculation to derive the spectral density of that noise, making use of this spectral density for the shot noise of the incoming light. And in later lectures, you will meet spectral densities for all the other kinds of noise. This is the shot noise and the light. You'll meet spectral densities of noise due to seismic noise, oscillations of the ground feeding through a seismic isolation stack, spectral density of thermal noise, and so forth. This is our first example of a particular kind of noise in the gravity wave detector. Okay.